and you can treat, as I said, that you can treat E1, E2, E3, and so on, and En as the canonical basis or a standard basis for canonical basis for Rn. Okay? So this periodicity, okay, this periodicity is also, kind of said, or you can say actually that if your U kind of satisfy such a periodic condition, then your U basically lives on a torus actually. So you are living on a torus. Okay, I'll talk in a moment about it. Okay, so if your boundary conditions, if your U is on torus, then you will have what you call this periodicity condition actually. Okay, so let me give you a quick brief. Like this is the basic and important stuff actually. So what is important stuff? So you have this Navier-Stokes equation and these assumptions. So if your omega is open and bounded set, then your initial conditions are going to be, ux0, u0 x, and your boundary condition is going to be that, okay, for every x, the velocity agrees with a fixed function phi xt, okay, and if you are considering, say, full space Rn, or you are considering, say, omega to be an unbounded, then in this condition you have to add what do you call your you have to add what do you call your another condition actually that goes like this, that okay, asymptotically uxt goes to some function psi xt actually, okay, whether you go to x equal to positive infinity or x equal to negative infinity. And as I said that a lot of people, for the sake of simplicity, they also consider what you call the periodic boundary condition. And what do you mean by the periodic boundary condition? That the velocity has a period L in each of these ith direction actually. So in other words, that if your x moves, if your fluid particle is moving to what do you call in a specific direction, say in ith direction, say up to L unit, it will be returned back to what do you call to the same point actually. So when this is going to happen, like this is going to happen, like okay, when you are in, for example, a sphere, or for example when you are on a torus actually. Okay, so therefore you also call such boundary conditions as that you have that your U lives on what do you call torus actually. Okay, the boundary conditions from the torus. So this is what is the case. Let me write these some of these quickly. Okay. Here, for the sake of okay. So initial condition is ux0 equal to u0 x for all cases. So if omega is bounded in say Rn, where n is 2 or 3, then the boundary condition is uxt equal to a fixed function phi xt for all points x on boundary. So if you are staying on boundary, your uxt is a fixed function now. And if your omega is unbounded, okay, or full space, are you talking about what do you call full space, then along with this you need to have an assumption that uxt goes to some function psi xt, okay, whose regularity I'm not talking at the moment about it, as you go into what do you call asymptotically along horizontal axis, and if you are considering what you call, and the third kind of boundary condition is really what you call the periodic boundary condition situation, where ux plus LEI will take you back, okay, uxt, okay. So this means that you are sitting on a torus actually, okay, and you are living on a torus actually, okay. So these are going to be, usually these are three are the important conditions. Why I'm putting it here, because if I have to quote it, because I'll keep on rubbing what you call these boards, I'll keep on cleaning these boards. So these are the important facts that I'm putting here so that I can quote them again and again if I need. Okay. So we had discussion on what do you call the Navier-Stokes equation and its suitable boundary conditions. Let's talk about what do you call the functional setting. So now I'm going to talk about the functional setting for each one of these situations. The situation when omega, the region which the fluid fills, is bounded, the situation when it is unbounded, or the situation when you are sitting on a torus actually. Okay? So I'll talk about all three situations and what would be the functional setting and the meaning of a Stokes operator actually in each of the situations. Okay. So let me give some general notations. Okay. So say that, and these notations are for all three cases. In other words, that when omega in Rn, where n is 2 or 3, is bounded, omega is what do you call is R3, the full space, or the omega is the torus actually. Okay. Rn, or maybe the Tn, where n can be 2 and 3. So this notation is going to be generic actually. So what is the meaning of, say, Lp omega, the space of Lp omega Rn? Okay, so what does we mean? We all know that very well. So this is really the space of, called the Sobolev space of Rn valued p integrable functions. Okay, p integrable functions. So the shortcut for this will be used as simple LP. So whenever I write LP, I mean this actually. And the other interesting, for which I'll use, say for example, the notation WKP, which is basically the Sobolev space WKP. It takes input from omega and throws them in into Rn, so it's going to have what we call 2 or 3 vector depending on the dimension. As I said, I'll be interested in 2 dimension, solving this Navier-Stokes equation in 2 dimension. It's at least in weak sense. Okay. Then we know what do we mean by that. I'm not getting into the detail that, okay, what do we mean by that. So you say that this is the space of all those functions whose derivatives up to the order k, they all are p integrable. Okay, so in other words, u and u prime, you know, the derivative of u with respect to say x1, x2, x3, okay. So in other words, whose all derivative, all kind of partial derivatives, okay, the weak derivatives, okay, up to the order k are p integrable. Okay, so we know all this, so I'm just showing this directly. Okay. We will be particularly interested in L2. Okay. And for the L2, I'm going to use this notation as norm. Okay, so the norm on the L2 is going to be denoted by, say, this notation. This would be the L2 norm. Like I'm not going to put L2 here, so whenever I'm writing this, I'm going to mean L2 norm and L2 inner product, and the norm on the L2 is going to be simply denoted by, you know, this absolute value actually. So this is L2 norm, L2 inner product, and this is L2 norm actually. Okay. So for practically, I'm not gonna, you know, write all these. Okay. I hope you all remember, at least I can write that. Okay, if you have UV, then what does this mean? That okay, you take u of x and v of x, multiply them with respect to say dx, and integral all over actually. So this is what the definition of inner product is, and the norm on L2. Okay, so the L2 norm is basically, as I said, I'm not going to write this L2, so I'm not writing it, but you have to assume whenever I'm not writing something, I'm doing things in L2, the norm is in L2. If you take your u of x and you square it or omega, integrate it with respect to dx, okay, and 1/2. So this is what the definition of L2 is. So if you consider W K2, in other words, the space of all those functions, okay, space of Rn valued functions with their domain, with inputs taking from omega, okay, whose all derivatives, all weak derivatives, and mixed, all kind of mixed derivatives actually, okay, up to the order k are square integrable, we will denote such kind of space as, you know, as we denote usually as HK actually. HK. Okay? And in particular, we will be very much interested in H1. Okay? And what would be the norm on H1? Inner product on H1. So whenever I have to write the inner product on H1, I'll write this inner product H1. And what does this mean? That you take the inner product of UV in L2 and gradient U and gradient V in L2. Okay? And the norm in H1, I'll denote it by this symbol. I'll just write this. H1 is what is basically equal to square root of, what do we call, the norm of u square plus norm of the gradient of u square actually. Now consider the situation. So this is generic notation. Now consider the situation when you have, what do you call, the functional setting for the case when the omega is the entire R2 actually. Okay? It's unbounded and its entire R2, or maybe we'll call Rn. So in this case, I'm going to denote H by space of those functions, those vector fields, square integrable vector fields, taking values from omega to Rn, or maybe I can write Rn to Rn, where n could be 2 and 3 both, such that they are divergence free. Okay, they are divergence free. And for me, V in this situation is going to be H1 intersection H actually. So H1 is this space that I just wrote, intersection H1. In other words, this is the space of those functions whose for which the U and the gradient of the U are square integrable and they are divergence free actually, because they are intersecting with H, so they are divergence free. Okay, so this is what it is going to be. To complete these things a little bit more, let me write, I'll come back to this in a moment, but let me introduce an operator. Okay, this operator that I'm going to introduce is called the Leray Helmholtz operator, but I'll not get into the all tiny details of this Leray Helmholtz operator, projection operator, but I'll just give you the key picture of it and some of its properties, because otherwise this Leray Helmholtz operator that I'm talking about is a pretty abstract object actually. Okay, so here's the thing. Let me introduce Leray Helmholtz operator and return back to the functional setting. Leray Helmholtz operator. Okay, it's kind of a projection operator basically. It's a projection operator. So what we can do, here's the thing. So let me introduce this as a fact actually. Okay, well, there's a whole very rigorous mathematics behind it. I'm not getting into it, but I'm using this as a fact actually. So what does we can show that for any vector field U, we can decompose it into two parts. Okay, every vector field can be decomposed into two parts. One part is the gradient of some scalar field, let's call it Q, plus a vector field V, where the V is a divergence free vector field actually. Okay, divergence free, that is the gradient of the divergence of V is equal to 0. In other words, you pick any vector field, you can break it down into a gradient of some scalar field. Okay, there's an explanation behind it. Okay, what kind of a scalar field this is going to be, plus a divergence free vector field actually. So in other words, if you take a space of, you know, what do you call, a vector fields, you can project it onto, you know, a subspace, okay. So for example, you take square integrable functions. So you take the vector fields that are square integrable, okay. So what you can do, you can take a square integrable vector field and you can project it onto what do you call a space where, you know, one part, or you can project it on a space of divergence free vector field actually, okay. So that the entire L2 space can be projected onto the, what do you call, the space of the divergence free vector fields. In other words, for any vector field U, you can break it down into a gradient plus, what do you call, V actually, okay, where V is divergence free. So every U can be broken down into two parts where V is a divergence free vector field. So every U can be written as, so the key point that we have to keep in mind is that you give me a vector field, there is always a divergence vector field, okay, divergence free vector field, you know, and I can write U in the terms of that divergence vector field plus something, okay. This representation is not necessarily unique, okay, but it can be made unique actually. It's not big deal, but in its current form, it's not necessarily unique actually. It can be made unique with a little bit of more assumptions. So let me define a projection operator pi, okay, that do what? That swallows the vector field U and spits out what do you call its corresponding divergence free vector field, okay. So in other words, pi of U plus, you know, pi of gradient of Q plus V is what do you call equal to V, where V is the divergence field free vector field corresponding to the U. And here are, and this projection operator is basically called the Leray Helmholtz projection operator, okay. Why we are interested in this projection operator? Because this projection operator, we're going to apply it onto what do you call our Navier-Stokes equation, and our Navier-Stokes equation will become an equation that you usually deal, so it will become what do you call the kind of equation that you have encountered previously in your courses. So it become what do you call partial U by partial T, okay, U by dt plus AU plus some function of U equal to some another function of what do you call T actually, something like that. So it goes in the standard form actually, okay. So we'll do it in a moment. So this would be helpful, okay. I can put basically notes if you're interested in going into the mathematical rigorously into this stuff actually, but that's not my key thing that I want to do today. Okay, so the partial U of U is this. So what are some of the properties of this projection? Okay, so the first property is that this projection is indeed a projection. In other words, that if you operate it pi onto what do you call pi U, you're gonna return to pi of U, okay. And the second thing is that the divergence of pi of U is 0. Why? Because pi of U is V and the divergence of V is 0 for sure, which is something trivial. And another important property is another property of the projection operator is that if U is divergence free, that is U is already a vector field, U is already a vector field for which the gradient of U is 0, okay, then U will be projected onto itself. Okay, in other words, that the U would be equal to U plus what do you call 0, because U is already divergence free actually. Okay, so this is another part of it. The third thing is that if you apply your projection operator onto what do you call the gradient of del Q, you're going to get a 0. Okay, so the pi of gradient of Q is what do you call it? 0. And what? Another small thing that I must add is that fourth one, that the pi operated onto say partial U by partial T is going to give you back partial U by partial T. Okay, so treat all this portion as facts actually, which require a fair amount of what do you call time if you want to get into the detail. But since Navier-Stokes equation is not our topic of this entire subject, but what we are mainly interested in, okay, so why I'm doing Navier-Stokes equation, because I want to study the long-term behavior of the Navier-Stokes equation. But what I wanted, okay, one approach could be that I just write Navier-Stokes equation and write a theorem about its long-term behavior. But what I want that, okay, Navier-Stokes equation is such an important equation, so I should give you some kind of a, what do you call, the fragrance or the smell of the Navier-Stokes equation. You should have some kind of at least some basic intuition for the Navier-Stokes equation actually. So therefore I'm not getting into the rigor. Alright, so let's return back to our full space condition. I mean, if you see, H here is what? H is the collection of those vector fields which are divergent field. So the projection operator in this functional setting is going to be an operator that swallows a vector field that is a square integrable and spits out what do you call a vector field that is divergence free actually. Okay, that's abstract Helmholtz operator, projection operator, while here I'm talking about a concrete one. Now, in this situation, let me define the so-called Stokes operator. Okay, so-called Stokes operator. So the Stokes operator is what? So Stokes operator, I'm denoting it by A. So it's an operator A which swallows a value from domain of A and it spits out a divergence free a vector field, and it is where the domain of A is H intersection H2 of say R2. In other words, that domain of A is the collection of those divergence vector field whose all derivatives, all partial weak derivatives up to the second order are square integrable. Okay, and the definition of the what do you call this Stokes operator is that it is the negative of the projection of Laplace U. Okay, why you need H2? Because you want this Laplace to make sense actually. Okay, so the AU is a negative projection operator operated on Laplace U actually. So in my equation, in Navier-Stokes equation, so what I'm going to do, I'm going to take this equation and operate this Leray Helmholtz operator on the both sides. So that the projection operator of partial U by partial T is going to be partial U by partial T. This is going to be something that I'm going to talk in a moment. So this term is going to be what? Nu projection operator operated onto Laplace u, so it's going to become AU, okay, and this is going to be 0, okay, and this is going to be the projection of f actually. So what can I do? So I can rewrite this equation in our standard form of the evolution equations actually. Okay, this is what that I'm doing. So the Stokes operator is operator with the domain this, and its definition goes like this. And here are some of